This meeting is being recorded.
Hey everyone, how are you? I see people coming in. Do I have an audio connection? Just double checking with the class. Yeah, we do. Okay, that sounds good. And the YouTube stream is also going live. Let's go ahead and start soon. I see everyone's coming in. We're getting close to the end of the semester. I understand that we're close to the end of the semester because I also see people already emailing me about next semester. So are people already starting to register for courses? Yes? Sort of? Actually, when's your date? I mean, everyone has different dates. Is it freshman last or first, or how does it work? 4.
December 4th?
Oh, you said December 4th?
Yeah.
Ah, okay. So you still have a...
For me, I don't know about
You have a while to think. Okay, because somebody already started emailing me about my class next semester. Actually, with regards to all of these different classes, I guess, is Carnegie Mellon still doing something with the math department where there's some kind of a session where students share their experiences with classes? Oh, has that happened? Has that already happened?
students.
No? Because there's usually something which John Mackey hosts, which is really interesting, where students kind of share their experience about all of the various classes as people register. But, okay. Well, people are coming in. I just wanted to chat a little bit while people are still on their way in. Okay. So in that case, I guess I'll also say, well, when should I do that? Let's go ahead and do some problems first. So today we're talking about integer polynomials, and that's actually the handout that's on the website for this particular week. Let me switch to that. Just a second. So this is, if you go to the course website, then you can see it. It's over here. And integer polynomials, well, that's questions about polynomials and integers at the same time. So it's some kind of a mix between algebra and also number theory. And today we're going to play with a bunch of problems where we'll get to play with some of those things in both number theory and algebra at the same time. The warm-up I want to do today is the first question on the sheet, which says, let p of x be some polynomial. It's just x minus a times x minus b times x minus c times x minus d. Assume that px equals 0 has 4 distinct integral roots, and suppose that px equals 4 has an integral root called k. And you're supposed to just show that k is the average of a, b, c, and d. As usual, if anyone has any ideas, feel free to just type raise hand into the chat, and then we'll go from there. You don't have to have the whole problem solved. In fact, it's no fun if you do. Any ideas on how you might try to attack this? Actually, while people are making ideas, I'm just going to copy the question onto the other screen. It's just p of x is this product, x minus a, x minus b, x minus c, x minus d. And that's all the question's telling us. Oops. P of x is equal to x minus a, x minus b, x minus c, x minus d, 4 distinct integral roots. I'm using z for integers, integral roots. And also you know that p of x equals to 4 has, is it a unique or is it an integral root? Let me just double check what we've got here. It has an integral root k. Okay, we don't know that it's unique. It has an integral root k. Show that k is the average of a, b, c, and d. Okay. Any ideas? You can put any small idea too. It doesn't have to be like big idea. Really, even small idea is okay. We'll build from there. Jack.
Okay, this would be a very full disclosure. I don't think this is a good way.
Doesn't matter. Just tell us.
we could distribute each one of them and then subtract 4 and then try to pull out x minus the average and see what happens. It would be...
Oh, okay. I understand what you're saying. You're like, okay, p of x equals 4. That's... I see what this is. Let's just write down what you meant, okay? What you were going to say is like, look, if p of x equals 4 has a root k, that implies that if I took the p of x minus 4, it has a factor x minus k. Is that what you're trying to say?
Yeah.
Yes. So then you were like, okay, what if we just distributed this x minus a, x minus b, x minus c, x minus d, subtract 4, expand, try to factor out x minus a plus b plus c plus d over 4. Is that what you're going for?
Yeah.
Okay.
Like,
That's
I don't know if that would work, and that would probably be a lot of work, but...
okay. But you also said something else useful there, which is like, it feels like this would be a lot of work solution. So usually whenever you come up with this, you write it down. It's a brainstorming. You write it down. And then you note to self, let's see if we can be lazy first. See if we can find any other way. If we can find some other way, we try it. But if we can't find anything else, we can go and do this too. That's actually how I solve every problem. More thoughts. And as you can see, just say whatever you're thinking of. This is how we solve this question. It's not supposed to be like a just look at it and solve it type question. Aha, another idea. Let's see. This is Raid.
I'm not really sure, but probably we can use the rational root theorem. If k is the solution, then it must divide a, b, c, d minus 4, I guess.
Ah, okay. So the rational root theorem, right? Let's do the big expand. If you did the big expand, because we're building off of this idea, x minus a, x minus b, x minus c, x minus d, minus 4 is going to have the form x to the 4th, then like plus some stuff in between, and the constant term happens to be a, b, c, d minus 4. Now the rational root theorem, in fact, in this case, the rational root theorem says any root which happens to be rational has to be a factor of that. Actually, since there's no coefficient on the x to the 4th, the only rational roots are integer roots. Are people okay with this? Rational root theorem is like rational root must have numerator divide the last thing, denominator must divide the first thing. And so what does the rational root theorem say? What does it say? Rational root theorem implies every rational root is in fact an integer root. It's an integer and divides this a, b, c, d minus 4 multiplied together thing. That's true. So whenever we solve a question, we just collect true facts and we see, can we use it for something? More ideas. I see another hand. Jack.
Okay, so kind of along the same line as this, but instead of looking at the last term, looking at the x to the 3rd term.
Oh.
We could see that the only times that you multiply all of them together to get x to the 3rd is when you multiplied by one of the constants each time once. And so all of the x to the 3 terms would just be the constants.
Yes. Do you mean this?
Yes.
Right? So in some sense, the sum of the roots is the minus of the coefficient of x cubed. Because the only way to make an x cubed is you must pick the x 3 times. And so you pick the not x once. And that's how you get an x cubed. And this minus 4 at the end is not going to change anything. The minus 4 won't give you an x cubed term. So that's true. And I assume you like this because that looks like a plus b plus c plus d.
It does look like a plus b.
Okay.
I don't know if that's useful, though.
We never know if it's useful until we keep going. So that's cool. Actually, since you said it's like a plus b plus c plus d, I'm going to do a very slight edit of this. And I'll write minus of this. That's why you got excited. Okay, more ideas. These questions are fun because you can use anything from algebra or from number theory. And it's supposed to be hard, but we have to just keep throwing new ideas out at this before we crack it. Aha! Is this George?
Hello. I was thinking maybe using Vietas. So like we know P of X has like 4 integral roots. So the sum of the roots has to be integral.
Okay, so we have this like Vietas theorem, right? We know that the sum of the roots is an integer. That's true. And this Vietas theorem is telling you, I think you were inspired maybe a little bit by this thing. It's like Vietas theorem tells you that the sum of the roots is minus of that coefficient of x cubed. And actually, along this Vietas theorem lines, oftentimes what you use with Vietas theorem is the sum of the roots and the product of the roots, right? And the product of the roots of P of x is, in this case, just the constant term of P of x. And that's because you're going to, in order to make the constant term, you actually have to pick the not x from every one of the parentheses. So you get minus a times minus b times minus c times minus d. The number of minuses is an even number, so it just becomes plus. And that's how you get that. And we could also use Vietas theorem to get weird other stuff. You can get like the sums of all ways to pick 3 roots and multiply them together, and so on. And that will give you like the x squared coefficient, and so on. Okay, more ideas. Ideas can build on stuff that we have, or it can be fresh. And really don't worry even if your idea feels small. Even if you put a small idea, there's a chance that someone else will build on it. Raise hand, Jack.
Okay, so I was continuing off number 3 and saying that when we have that P of x minus 4, the expanded version, we could break it. We know there's at least one root, so we could break it down into x minus k times, and then something of the form a x cubed plus bx squared plus cx plus d.
Okay, let me write this down, right? So what we have here, oops, froze, just a second. I'll just restart my drawing program. One moment, please. Okay, great. So what you wanted to say is, let's say step 5, you were going to say the P of x minus 4 has to be writable as x minus this k, whatever it is. And in fact, the leading coefficient will be a 1. It will be x cubed times something, because it's going to be an x to the 4th plane. I won't use the a because those are taken. Let's use some Greek letters. By the way, that's why people use Greek letters. It's so that you can have more letters. Plus beta x plus gamma. Is that okay?
Yep.
Yeah, so that's true. You can definitely you have to be able to factor it this way, and that's where k is a solution. K is a root.
Do you want me to keep going?
Go for it.
So my next idea was that we could look at expand that specific thing out and look at the x third term.
Oh, interesting. So we'll get an x to the 4th, that's for sure, right? That's the first term when you multiply those. How much x cubed do I get? Well, the x cubes I get are, I'll write plus and then something times x cubed. I think it's alpha minus k. Is that what you got?
Yes.
Because to get the x cubed from this x, I can take an alpha x squared, and for the minus k, I can join with the entire x cubed. And then there's like more stuff. I'll write plus dot dot dot. Okay. And are you trying to use the fact that the alpha minus k, that's supposed to be this minus of the sum of a plus b plus c plus d?
Yes.
Okay, we know that too, right? We happen to know from the step 3 gave coefficient minus a plus b plus c plus d for x cubed. So you have an equation. It's that alpha minus k is equal to minus of a plus b plus c plus d. That's true. Gee, it's tempting. It's like I have a k supposed to be the average, and I just need to know something about this alpha. Okay. Any other ideas? Ooh, I see an idea. Joseph.
So I was thinking from like a number theory standpoint. So k is an integer and ABCD is an integer. So if you plug in k, you're multiplying 4 integers, and that has to equal 4. So
Just a second. Let me get this straight. So you said k is an integer. Are you starting from any of these, or are you going on your own direction? Which is totally fine.
It's my own direction.
Your own direction. So what are you trying to do here?
So k is an integer.
Yes.
And A, B, C, D are also integers.
Yes.
Which means each of those factors are also integers.
Yes.
So when you plug in k, you have to get 4, which means that those factors are like super.
Okay. So what you're saying is, hey, what if I just look at this thing? I'm like, if I plug a k in, I'm supposed to get 4, right? So I'm supposed to be multiplying k minus a, k minus b, k minus c, k minus d, and getting 4. Let's go there. What happens there? So what you're saying is, look, p of k is equal to 4. So k minus a, k minus b, k minus c, k minus d is equal to 4. Okay, that was a great idea. I think you have a good idea. And at this point, I'm going to say, does anyone else want to continue that idea? Because I know you've got something. And by the way, there's nothing wrong with what else we were doing. The way you solve a problem is you flail around for a while, and you see that some of the things you use. I see Adavit.
Yeah, so now we want, since A, B, C, D are distinct, that means k minus a, k minus b, k minus c, and k minus d are all distinct. And we want 4 distinct factors of 4. And so the only way to do that is minus 2, minus 1, 1, and 2.
Yeah. So somehow it's like, how can you multiply 4, not just distinct, also distinct integers? How do you find 4 integers that multiply together and are all different and make 4? There isn't much way. It's like, you can't go and use like 4 to do it, because you'll have too much like, well, you just only have 2 like 1s, a plus 1 and a minus 1, right? And so the only way to do it, to multiply to 4 is with like minus 1, plus 1, minus 2, and plus 2. Okay. Now that's pretty powerful. Now I know that this k minus a, k minus b, k minus c, k minus d are this like minus 1, plus 1.
So there
Yeah?
you go. Set k minus a equal to minus 1, k minus b equals 1, k minus c equals minus 2, and k minus d equals 2.
Okay, so you're using this important
add
thing.
them all up and divide by 4 and you're done.
Yeah, okay. So you were going to say, without loss of generality, you have that k minus a is equal to minus 1, k minus b. It doesn't even matter what order you use, because you're about to add them all. Minus 2, k minus d is equal to plus 2. And then if you just add everything together, you get 4k minus the sum. A plus b plus c plus d is equal to 0, which is exactly the same as k being the average of all of them. So this means k is the average. A plus b plus c plus d all over 4. And so that's the fastest way to solve this thing. But again, as I emphasized, the way we solve any of these questions, we have to just kind of throw ideas at it, and after a while, something like jostles, and that's what happened here. So this was kind of cute. When I did this on the previous class on Wednesday, somebody said, last time when I wrote on my concepts homework, it's obvious, I lost 10 points. So, well, here's the Putnam. So on the Putnam, this part is considered obvious. This is okay. Oh, I should say, at this point, I want to make a few comments. One thing is that the Putnam is actually going to happen. I'm not sure if people saw this. I don't think you would have seen it. I just got an email because I'm the one who's in charge of it for CMU. But the Putnam is going to happen in February. I think it's like either February 20 or 21, something like that, whichever is a weekend day. I believe it's usually Saturday. Actually, I don't know if it's a weekend this year, this time. But then in any case, it'll be in February, middle of February. And the way it works is that people will be able to take it remotely. So I do hope that you guys will enjoy trying this out. It's going to be an informal competition in the sense that you can do it on your own time. They won't be giving particular prizes this year because unfortunately there's no proctoring. However, if you enjoyed this class, that will probably be something interesting to do, and afterwards you definitely will be able to, we can get together and have a chat about how the questions are. So the Putnam is going to happen, and it's going to be in February. The other public service announcement I wanted to make is that the reason why the Putnam is remote is because unfortunately COVID is a thing. So I'm just going to make this public service announcement. If you are on campus, please be careful. The situation outside in Pittsburgh is getting quite intense. I'm not sure if you guys are following this, but a few hours ago I got a phone call from the school district because I have kids going to school, and the school district said they just flipped to everything remote. So I'm not sure if you guys know this, but the University of Pittsburgh, which is our neighbor, has also already gone into shelter in place. So everything around this is actually kind of tightening up. Along those lines, I'm going to say, if any of you are living on campus, if you haven't downloaded the Novid app yet, please do consider joining it, because this is one way that we're trying to keep everything together. And if you don't know yet, what the Novid app is trying to do is it's trying to give everyone a radar, so that if these things are coming into our community, we'll at least be able to see it. I've been pressing this quite hard recently because of the fact that it's getting hot here in Pittsburgh. So if anyone has any questions about that at the end of the class, I'm also happy to answer any questions. But I just wanted to emphasize to everyone, COVID is actually a pretty serious thing. And I mean, I and many other people are trying to work as hard as we can to make sure that we make it all the way through Thanksgiving, and that when people go home, you bring only yourselves and not additional viruses to your family. So please do be careful. I was shocked yesterday when the number of cases in Pittsburgh area was 412 That was like 412. I can remember that number, obviously, because that's the area code of Pittsburgh. That was like strange irony. But somehow that is the number of cases in 24 hours yesterday. That were reported yesterday, 412. And just to put this thing into perspective of how big this is, I didn't realize it until I was talking to the Putnam class the other day. And I was like, wow, that means that in 2 days, because we're getting about 400 a day, in 2 days, the number of people who got COVID in this area, this small city, was the same as the number of people who went to my middle school, which was like 800 people. And once I put that in perspective, I was like, wow, it's really everywhere. So please be careful. Please be careful. Yes. And if you haven't installed Novid yet, please do join. And please also, if you happen to unfortunately get positive, please do report through it, because we're really trying to keep everything open here. I'm actually right now most afraid that, say, someone at the city level or the county level will actually just order everything to shut down. And what we would like to be able to say is that you shouldn't shut CMU down. We have ways to keep ourselves open. So that's what I'm trying to do. Anyway, we got some time left. Let's play with another question. The other question is actually a quite hard one, but it's also very interesting. And so I want to start. I want to do as much of it as we can in this class. It's question number 3. So question number 3 says, I've got a polynomial, it's got degree n, and let's assume, wait, how can I scroll this so it's just right? I'm a bit of a perfectionist, so I like it to be just right. So we have, okay, anyway. So the question 3 is what I want. Polynomial with degree n, and let's assume that it's an integer polynomial. In this case, integer polynomial is not going to mean polynomial with integer coefficients, nor is it going to mean polynomial with integer roots. It's going to mean it's a polynomial where if you stuff an integer in, an integer comes out. So now what we're supposed to show is that every coefficient, if you multiply it by the degree factorial, is an integer. Actually, this is a hard question. And so I really want to also dive into what this means, because it's kind of nifty. You see, at first glance, if somebody tells you, I have a polynomial, you put an integer in, you get an integer out. If a person is a bit more naive, they might be like, oh yeah, so that means that all the coefficients must be integers. But after you take a bunch of math classes, you know that weird stuff can happen. You know that somehow it's possible to add 2 irrational numbers and get a rational number. I'll give you an example. If I add minus square root 2 and plus square root 2, bingo, it's rational. But that's like really dumb. Okay, but I mean, in any case, it's like in this question, it's like, well, you know, just because integer in, integer out, that's not automatically going to give you that all the coefficients are integers. But the nifty fact is that it turns out that it's not that far off. If you just multiply all the coefficients by n factorial, the degree factorial, bam, then they're integers. So they're kind of close to being integers. And that's the question. How to show something like this? Integer in, integer out. Oh, before we go and show something like this, I want to go and see if, does anyone have an example of a polynomial that has integer in, integer out, but that the coefficients are not integers? Because like, it would be nice to know that there are such weird polynomials, or else we just wouldn't even need this statement, and we'd just say integer in, integer out means all coefficients integers. Anyone have an example of a weird polynomial that gives you integer in, integer out, but the coefficients are, so I see, is that John? John what? John.
I think maybe like x times x plus 1 over 2.
Ooh, so we have an example of a weird polynomial. X times x plus 1 over 2. Now, how do you know that that's, oh yeah, I'm going to write this way. A lot of people in this class have taken a concepts of math class or are taking it. If I write this, it means it takes integers in and it sends integers out. Why? How do you know it's always an integer?
I guess one of them will be even.
Because one of them will be even. Since at least one of x and x plus 1 is even when x is an integer. So that's an example. This is an example of a weird polynomial where if you put in an integer, you get an integer out, but the coefficients have like halves in them. So that's one example. Are there any other ones? So that's an example of a quadratic. Does anyone have an idea of one that we can do for a cubic? Just so that we know we're proving something about weird stuff. We have lots of people. Rajiv.
So using similar logic, perhaps, you could take x times x plus 1 times x plus 2 over 3.
Okay. So you could do this over 3. And that's going to go integer goes to integer. Since I'll write 3 divides at least 1 of x, x plus 1, x plus 2. But we can go further than this. So we don't have to only divide by 3. What else could I divide by?
Divide by 6.
You could divide by 6. So I could change this to 3 times 2. Because, 3 divides at least one of those. And 2 divides at least one of, well, actually, it definitely divides at least one of all 3 of them. But like with the first 2, I'm already done. All right, so we just did something for cubic. Anyone want to give me one for quartic?
Well, you could do a similar.
Okay.
And you can.
But what are we going to divide by?
Divide by 4 times 3 times 2.
But how do you know? It's getting harder.
You have 2 multiples of 2 in there, but one of them has to be a multiple of 4.
Okay. So Elevate's like, we can do this by being more sophisticated, right? The way you be more sophisticated is like, all right, the 3. The 3 is the easy one. Of course, like one of the first 3 things will be divisible by 3. That's fine. And now the thing about the 4 and the 2 is it's actually true that whenever you take any 4 consecutive numbers, one of them is going to be divisible by, well, 2 of them are, half of them will be divisible by 2. All right, no matter what, if you take 4 consecutive numbers, half of them will be divisible by 2. But among that half, one of those will be divisible even by 4. The way I always think of this is because I grew up in America, we use the imperial unit system, which is the inches, right? And if you look at an American ruler, the American ruler is like the inches are these long lines, and then the half inches are these, I guess, half long lines, and then the quarter inches are these next things, and then the eighth integers are like a little bit shorter. Do people know what I'm talking about? Like if you look at the ruler markings in an American ruler or English ruler, and if you look at it, whenever you go to any 4 consecutive ones, you'll see a pattern where it's like, if you've got Like every other one, it spikes a bit longer. And it's like you have a spike that's longer and a spike that's even longer. So that's a true fact. So this thing actually also works. Z goes to Z also. Okay, is there an easy way to generalize this? Because what we're doing now is we're sort of making examples of all of these different polynomials which have different degrees. They all look kind of tantalizing like this. But at the same time, we're getting kind of tired of making these arguments. Like, what if I wanted to have the one for 1,000? Do we really want to do that? Is there another way? In particular, I claim that if you do it for 1,000, it's also okay. If you do x plus 1, all the way to x plus 999, that's 1,000 terms on top, divided by 1,000 factorial, it is also z goes to z. But is there a good reason why? Anyone want to raise hand? Ooh, I want to give people a chance, different people if possible. I'm just curious, Matthew, were you trying to answer this question or the previous one?
I mean, the previous one, I was just going to kind of generalize it to the form like the product of, like from, for example, k equals 0 to n minus 1, I guess.
Yeah, from k equals 0 to k equals n minus 1. Yep, and then divide by...
Yeah, x minus k and then divided by n factorial.
Yes. Okay, so you're generalizing this. You're like, we're sophisticated here. We don't even need to use a number like 999. You wanted to say x plus n minus 1 all over n factorial. That also goes z to z. But why? So all of these work out of it.
So you could look at the prime powers dividing the top and the bottom, and you'll see that they're more in the top, or like greater than or equal to number in the top than the bottom, so that you always get an integer.
So yes, if you analyze by primes, like the number of powers of each prime, that would work. That proof is a bit longer. So I'm curious if there's another way. I see that Erica has an idea also.
Oh, I was just going to say that when you have some number and you add the numbers like 0 to n minus 1 to those, that you're kind of going to get every number within that range, kind of like in the modular arithmetic of like mod n, you're going to get every number within that range. So when you multiply all of them, you're going to have one number that's divisible by like each number in the range 1 to n. And so then multiplying all of those together, you're going to have a factor of like n factorial.
Okay, so you're sort of like reducing things modulo n. You're sort of saying like, hey, if I look at the numerator, I have all of the different remainders modulo n. That's actually true. I get an entire string. And the denominator, I've got all of the remainders modulo n also. That's also true. The part that makes it harder to complete the proof that way, though, is that if I just know the numerator and the denominator are the same modulo n, I don't yet know that I can divide one over the other. I mean, we might be able to finish a proof that way, but we can't. It's not like immediate yet. So like out of it, your thing needs a little bit more still. Erica, yours also. This one would be a little bit hard to completely close. I'm just curious if anyone else sees like a quick way, because there's also a quick way. So let me see. My vision is bad. Autumn.
I was just basically going to say that for any number in the denominator, you can pair it with some number in the numerator that it can be divided evenly.
Okay, so if you can always do some of this pairing, you'll be good. The only problem is that also doesn't completely always happen. I'll give you an example. Well, actually, no. I'll give you an example which might help to jog people's thinking on what I'm trying to do here. Like, here's an example of something where it's hard to directly pair. How should I do this? You can see I'm just thinking in my head. I wonder if this will work. 101. Wow, maybe you can always pair? I don't think so. Wait a second. Let me try something. Yeah, let's try this. 2 times 3 times 4 times 5 over 4 times... No, you can! What? No. So I'm like, sometimes you can't. That was a bad example. I was trying to make up something else. 3, 4, 5, 6?
Wait, what if you do like 10, 11, 12, 13?
Okay, let's see. 10, 11, 12, 13.
What are you going to pair with 4 and what are you going to pair with 3?
Oh wow! How can you be so quick? Okay, yes. So I was like, I know from experience that sometimes you can't cancel that way. But there's a reason I said I know by experience, because I've done this before. I don't know if anyone gets the hint of what I'm trying to do. I'm like, I've actually done this kind of thing before in my life. I see a hand. Is it AJ?
These look sort of like n choose k.
Yes, they're chooses. This is choose. This is 13 choose 4. Bingo. So that's the deal. Like every single one of these is a choose. Chooses are integers. Because it's like, how many ways are there to pick something? Of course it's an integer. I can't say like the number of ways to pick 4 things from 13 things is like 37.6. No, it's an integer. It counts something. And so that's like a beautiful fact. It's that this thing counts something. Here's the formula for how you count it. How do you prove that's the formula for how you count it? Well, you just say, look, if I want to pick 4 things, there's 13 ways to pick the first one, 12 ways to pick the second one, 11 ways to pick the third one, 10 ways to pick the fourth one, and I have repeated my picks like 4 factorial times because I can like rearrange them. So that's actually the proof. That's the simplest proof. Everyone else who had ideas, you could possibly have turned those ideas into a proof. But over here, the easiest thing is just to say these are all chooses. So that's kind of cool. We have just found out that all the chooses, x choose n, is actually a polynomial, right? X choose n, if you think of it, is a polynomial in x. And it always takes in an integer and it spits out an integer. That's what we found. General, I mean, it's written here as x plus n minus 1 choose n. But I could actually just say, simpler is just be like x choose n are all polynomials which go from integers to integers. So that's cool. And it also is kind of satisfying that there's like this n factorial in the denominator. Okay, so now we've played a lot with these things. We've just found out a whole variety of these weird polynomials that send integers to integers, but they turn out to be not that weird. They're all chooses. The next thing is, something, question, yes. Mozzie.
Yeah, I had a question about the one in yellow. Why does it go directly from x plus 2 to x plus 4?
Because I screwed up. Okay.
Oh, okay. Thank you.
Thank you. Please call me out on that fast. Yeah, this is liable to happen. Because every time I do this stuff, I'm just doing it based on the ideas that I hear from the audience and some things I throw in. So yeah, it happens. Thanks. Okay, so now the thing I want to hit next is, this is nifty. Somehow, like these are all of the, not all of them, these are all a bunch of different ways to send integers to integers. But now I want to go and try to solve the problem. And this particular one, I want to use a method which is actually also on the sheet somewhere else. It has a very long name. Oh, I probably shouldn't have said that. But anyway, let's see what we can do to try to solve this question. The question now is, let's suppose that we send integers to integers, and the sheet has some stuff on it. Maybe I should actually put up the sheet since I already dropped the hint, and we'll also have to go and prove that thing. But we should use one of these things with a long name. We should either use Vandermonde determinant, or we should use Lagrange interpolation, or maybe we can use Fermat's last theorem. You can decide which one of them is the least likely. But I want to spend some time on this, right? It's like it turns out that this is useful. Anyone want to throw an idea out of it?
All right, so if we throw Lagrange interpolation at it, we just set, well, our polynomial is n degree. What if we choose n plus 1 values in the domain and, like, say that they map to integers? And I guess just based on this Lagrange interpolation, you could just grind out the coefficients.
Okay, so the thing here is, like, the first time I ever saw this polynomial, I said, what is this? This is a very, very, very big thing to stare at, and it's very hard to read, and it's not clear what the heck is going on. So let's actually do an exact example. It's like, well, I want to have, let's suppose I have a polynomial that takes in integers and spits out integers, okay? And we want to figure out an expression for all the coefficients of that polynomial, or rather just like write down that polynomial, okay? So let's suppose that p of x has degree n. And don't worry about that formula for Lagrange interpolation. We're going to get it here. We're basically going to derive that formula and then use it. So suppose p of x has degree n and sends integers to integers. the way Lagrange interpolation works is that you need to have n plus 1 points, and then you use those n plus 1 values of points in order to get an explicit polynomial that lets you run through all of those points. This is like how not to do your physics homework, or any actual experimental science. In experimental science, you do this like least squares regression line. In mathematics, we say, I got all the points, I want to go through all the points. Okay? And the way you go through all the points, we got to decide on some points. Which n plus 1 x coordinates might be convenient? Anyone else want to try to hit this? I want to see if anyone else wants to get involved in helping to suggest the idea. Otherwise, we'll go with Adivate again. Anyone else want to raise the hand and suggest n plus 1 different inputs? It's very hard to go wrong. You can do it with virtually any n plus 1. Well, not virtually any, but like virtually any convenient n plus 1 inputs is going to do something for you here. If not, then Adivate, what would you want to throw in for the n plus 1 inputs?
0 to n.
0 to n, good. Not 1 to n plus 1. So you're speaking like a proper computer scientist here. But 1 to n plus 1 is not nice because there's an n plus 1. So the points you want to throw in are 0. I'll use this notation. This is the maps to notation. I'm not sure if you saw this in the concepts class too. It's like 0. This symbol means it will map to. It goes to something. I don't know. Goes to something. I guess it goes to A. And then 1 goes to something, goes to B. 2 goes to something, goes to C. All the way to n goes to something. Clearly it goes to n. Well, no, that just goes to something. Okay? You know what? You shouldn't use A, B, and C. You should actually go and use like B sub 0, B sub 1, B sub 2. Now they have names. Okay, great. So I've got all of these names. And now from this, it turns out it's possible to write down a polynomial expression. And now I want to kind of deconstruct this Lagrange interpolation formula. Here's a term of a polynomial. One term of the polynomial looks something like this. X minus 1 times x minus 2 times all the way to x minus n divided by 0 minus 1, 0 minus 2, all the way to 0 minus n. That's one part of the polynomial. I'll actually adjust it a little bit. I'm not done yet with this piece. But I'm going to also say another part of it will be x minus 0. Now it skips the x minus 1 term. X minus 2, x minus 3. I'm just emphasizing that you have everything except x minus 1. But now, on the bottom, I do 1 minus 0, 1 minus 2, 1 minus 3, all the way to 1 minus n. And the last term is going to be x minus 0, x minus 1, all the way to x minus n minus 1, all over. It'll be n minus 0, n minus 1, all the way to n minus 1. All right. This is not done yet. This is a bunch of stuff. But I want to see if other people can help me get this formula, okay? Because the thing is, like, there's a big, messy formula, but it's a lot easier to kind of pick it apart one piece at a time. This is not the answer for the polynomial that goes through all of this, but it's pretty darn close. Can anyone else tell me what's interesting about the way I constructed this? In particular, if I plug in x equals 0, can you tell me what happens? And why? Maybe that's why the terms look like this. Anyone else want to raise hand? There's something special about the way all of these products were written in the numerators. A hand. Matthew Garcia.
Yeah, I was going to say if you plug in x is equal to 0, at least for the first term you... Oh, wait. I mean, the first term you'll get 1. Wait, I didn't think this through for the other terms, though.
Okay, but this is good. Okay, can anyone else build on this? So Matthew Garcia says, hey, check it out. And by the way, this is not my answer, but it's just like, the first term gives you 1. That's cool. But what about the other terms? What if you plug in x equals 0? I see AJ.
They all give 0 because they have an x minus 0 term.
Yeah, they all have an x minus 0, right? So if I plug in 0, everything else is gone, and I only get that term. That's kind of useful, but that's wrong. I'm supposed to have that this polynomial spits out the value b0 when I plug in x equals 0. So how can I fix it? This is not the answer. I need to still add some, I need to insert some more letters. In particular, there's no b0 up to bn here, so you better have them somewhere. Anyone want to tell me what to do with this? I see there's, is it Matt?
So the b's should be the coefficients for each term?
Yes. So let's multiply this by b0. And let's multiply the next one by b1. And let's multiply the last one by bn. Now it's just magic. If I go and plug in 0, the top one, the yellow thing, becomes 1 times b0. Yes, that's what I wanted. You plug in 0, you get b0, and the rest of them are all 0 if I plug in x equals 0. If you plug in x equals 1, what happens to the top term? Well, you plug in x equals 1, there's an x minus 1 factor. Top term's dead. In fact, all the terms are dead except for the pink term, because the pink term's the only one that's missing x minus 1. But fortunately, if I plug in x equals 1 here, I get 1 minus 0, 1 minus 2, all the way to 1 minus n. And over here, I get 1 minus 0, all the way to 1 minus n. So it's perfect. It gets you a 1 times b1. Is everyone clear on this? This is like Lagrange interpolation is a very scary looking formula, but the only thing you have to remember is you just have to multiply together a bunch of x minus things where you take turns leaving one of them out. The denominator only serves one purpose, which is to make it so that when you plug in the x equals that thing that's left out, then it's all 1. Okay. So this, by the way, is actually the polynomial. We know that. This whole thing is actually p of x. So I should say, just from these n plus 1 values, I'm able to reconstruct the polynomial, and it turns out that the reconstruction is unique. That's why this Vandermonde determinant thing in the first thing was important. It turns out that if you have any n plus 1 values for a polynomial of degree at most n, that uniquely defines a polynomial. There's only one way to go through all of those points with a degree at most n. All right, so what this means is, okay, I started with a degree n, I got n plus 1 points. I was then able to deduce that that's the unique polynomial in this crazy expression. Now, how can I finish? Now I want to complete this. I want to show that if you multiply every coefficient by n factorial, I get an integer. Anyone want to help me complete this? Adivate.
Those denominators look kind of factorially, don't they?
They do, those denominators. What are these denominators? Okay, so I think what you're saying is rewrite the denominators like factorials,
Yeah.
right? Let's see.
It's like a factorial with one term missing.
Yeah. Okay, just a second. For some reason, my pen already canceled out again. We'll come back. Here we are. The drawing program I use is one that I recompiled from scratch and added various things to so that it would do my bidding. And it does, except that it crashes every so often. So now what we have here is that the bottom is like, it's like factorial missing something. Well, okay, let's see. So this first one, the denominator for the first one, that's clearly a factorial. That's like n factorial with minus stuff. It's actually minus 1 to the power n times n factorial. How about the second one? Second one is also like, it's missing something. Is that right?
Actually, no, it's like shifted.
It's shifted. Okay, I want to let someone else try, just to see. How would I want to write the second one? Well, the third one is where you start learning stuff. The third one is, it'll be like 2 minus 0, 2 minus 1, skip 2 minus 2, 2 minus 3, 2 minus 4, all the way to 2 minus n. You know what? I don't like how I drew it there. I'm going to write it somewhere else. I'm also going to take out this thing. I just want to know, if I had a 2 minus 0, 2 minus 1, skip 2 minus 2, 2 minus 3, all the way to 2 minus n, how might I want to write that as some factorial thing? Can someone else help me out? Rajiv.
So, I mean, you have your -1 to the respective powers, but you can write it as like 2 factorial times, so -1 squared times, or well, yeah, just 2 factorial, like positive, and then -1 to the n minus 2 times n minus 2 factorial, I think.
Yeah, there's an n minus 2 factorial here, and this is n minus 2. And I think that the 2 factorial does not need any minus 1s, because it's just 2 minus 0 times 2 minus 1.
They're just positive, yeah.
Okay, that's cool. Let's do the third one. Or in general. Actually, can someone give me a general form? General form would be like, not this 2, but like something else. What does it become? Anyone want to raise hand for this? General form would be like if I was in K's or something. Because I need to show that somehow whatever the general form is, that's the denominator, multiplying it by n factorial is good. Okay, I see Ra'id.
Yeah, so just going off this, I think it would be -1 to the n minus k.
Got it.
Times k factorial n minus k factorial, right?
Yes. Going up to k minus, oh no, k minus 1. Indices are hard. And then you skip the k minus k plus 1, all the way to k minus n. And that's equal to -1 to the n minus k. The power of patterns is great. Okay, k factorial, n minus k factorial. So these are all the denominators. How do I know that if those are denominators, I can clear them by multiplying by n factorial? I need to show that somehow you can clear all denominators by multiplying by n factorial. What does that amount to showing? I need to show something about every single one of these expressions. And what is that? Adavit. You're muted.
It's like the chooses again.
The chooses are back.
Like n choose k, just maybe with a negative sign.
Yep. The way you prove this is like, in order to show you can clear the denominator, you need to show that the denominator is a factor of n factorial. Right? I just need to show, that, don't worry about the minus sign, k factorial n minus k whole thing factorial is a factor of n factorial. But it is because n choose k is an integer. Bam! And that's it. Okay, so this question ends up being very related to n choose k binomial coefficients. And I'll just say the reason I put this here and the reason we spent all this time on the other things about the chooses is it turns out there's an even deeper fact. By the way, this is done now. We've solved it. But the deeper fact is it turns out that every polynomial that if you take an integer spits out an integer, it turns out those are all made from x choose things, just multiplied by different integers. That's a really cool fact. To prove that takes some more work. But it turns out that the things we found out over here, these are actually the building blocks of polynomials that take integers in and spit out integers. If you take any bunch of this multiplied by various integer coefficients, then that will be an integer to integer polynomial, and also vice versa. Okay, but that's a cool question. I just wanted to share this one with you guys. Hopefully this was somewhat interesting to you too. And I'll just wish you all a good weekend and please stay safe. It's pretty crazy out here. See you guys. I'll close out the YouTube. See you guys.